Today, we are going to give a precise meaning to limits. We are going to define exactly what getting close means. So far, when we've talked about limits, we've said things like, as x gets close to a, f of x gets close to L. But what does close actually mean? Before we write the formal definition, we need to understand how to measure closeness. Distance on the number line is measured using absolute value. This expression measures the distance between x and a. When we write absolute value of x minus a less than delta, it means x is within delta units of a. If delta is small, then x must stay very close to a. So delta controls the closeness in the horizontal direction, or the x direction. Delta controls how close x must be to a. This expression measures the distance between f of x and L. When we write absolute value of f of x minus L less than delta, it means f of x is within epsilon units of L. So epsilon controls closeness in the vertical direction, or the y direction. Epsilon represents closeness in the y values, or the output. Delta represents closeness in the x values, or the input. Epsilon is vertical. Delta is horizontal. Epsilon controls how close the output must be. Delta controls how close the input must be. Now that we understand how to measure closeness using absolute value, we're ready to define what a limit really means. We've been saying things like, as x gets close to a, f of x gets close to L. Now we're going to make that precise. We say the limit of f of x as x approaches a equals L if the following statement is true. For every epsilon greater than 0, there exists delta greater than 0, such that whenever the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. That means no matter how small you want the output error to be, there exists a delta greater than 0. That means I can find a small enough interval around a, such that the absolute value of x minus a is within 0 and delta. Let's say that in normal language. If x is within delta of a, but not equal to a, then f of x is within epsilon of L. Delta controls how close x must be to a. Epsilon controls how close f of x must be to L. Delta is about the input. Epsilon is about the output. Notice the order of the definition. First, epsilon is chosen. Then I must find delta. You choose how close you want the output to be. Then I choose how close the input must be. That order matters. Notice the 0 on the left side. That 0 means x cannot equal a. We are not including the point x equals a. We only care about what happens near A. That's why limits do not depend on the function's value at A. This is the goal. We want the output to stay within epsilon of L. The entire definition is about making this happen. If you give me an epsilon, I can find a delta. This is the heart of the definition. No matter how small epsilon is, I can always find a delta that makes it work. If that is true, then the limit exists. The limit exists if whenever x stays close enough to A, f of x stays close enough to L. And we can make that happen no matter how small epsilon is. That is the precise definition of a limit.